Hi guys, welcome to the Calculus 1 tutorials again. So basically, what we're going to be doing in this video is talk about the average rate of change. You guys might have seen this in one or more different forms, but we're going to be doing a formal definition of this, so as to help us define what a derivative is later on. So basically what I'm saying is, we've talked about linear functions, right? We know what y equals mx plus c looks like. It's basically just one straight line, and it has a particular gradient, and a y-intercept, which is represented by c. So that's really not too important to us right now. What's important is how we define the value of m, the gradient. And we all know how that is defined as. We know that this is equal to y2 minus y1 divided by x2 minus x1, right? And if you think about it, it kind of makes sense. If we have a line over here and we were to find the gradient is nothing more than the rise over run. So if this were a point x2, y2, and this were a point x1, y1, we'd simply be doing x2 minus x1 to find this delta x, the change in x as we move from this point to that point, and the change in y as we move from this point to that point. It's basically the same point, but this would be delta y. And what is represented by m is basically delta y divided by delta x, right? So keeping that in mind, we're going to be moving forward. We're going to be talking about this linear function and what this gradient represents and how this can be used to our advantage, especially when we're trying to define what derivatives are. Right, okay, so now we know how to calculate the slope. If we had particular values, we'd be able to find the slope. We know that for sure, if we had specific coordinates. So let's move on to a more formal representation of this. So what I mean by formal is basically, what if we have an axis over here and we have a weird looking function which is called f of x, right? And we know that f of x is basically moving from this point to that point. We could call these points you could refer to these points as different values, but at this point, let's just call this a. And we obviously know that at this point a, the value of y for this particular function would turn out to be f of a. And if we're at a point b, now we're talking about the x coordinates here, okay? So we would get a value of y which would be equivalent to f of b. So thinking about it, if we were to kind of zoom in to this particular scenario, then we'd get something like this. That's roughly equal to what I'm trying to explain to you guys right now. So it's f of b and b. So if we were to apply a similar argument over here and try to find the gradient between these 2 points, that would turn out to give us the gradient between these 2 points over here. And if you were to think about it, basically this represents the run part of the gradient. It's equal to rise over run, right? So this would be equal to delta x, and that would be equal to delta y. We know that the gradient of this line is represented by delta y over delta x. But there's a problem over here that you guys might have noticed at this point. This is a curve. We're talking about the gradient of a line. So what I'm basically saying is, the gradient represented by the points that lie from the beginning of the function to the end of the function in this particular interval would be an approximation to the gradient, if you think about it. Very close to the gradient if we were to zoom into this specific point, but not exactly equal to it because it's a curve. And that's another idea of a curve, that the gradient of a line is basically a constant. As discussed above, y equals mx plus c gives us constant, right? If we think about it, the gradient over here does not change. M is basically a constant. And the idea about a curve, it could be any curve, it could be a polynomial, it could be e to the power x, anything like that. The gradient of that particular curve is a variable. What I mean by that is, it's basically changing. It's not going to be a constant. And this is the underlying characteristic of a curve, that its gradient does not basically represent the gradient of the entire function. It would represent a gradient at a particular point. Let me show you what I mean. So basically what we're talking about is finding the average value or the average rate of change of a particular function. That would be represented by what we talked about earlier. So if this were the curve, we'd have rise over run, right? And we'd get the gradient of the line joining the beginning of the curve to the end of it, right? And that would be represented by delta f divided by delta x. Now delta f is basically the change in the value of y, or basically the value of the function at b and a. And we obviously know what's going to be the run part of this, right? So this is rise over run. I'm repeating this because it's a very important concept. And the run part is going to be delta x, which in this case is b minus a. So this kind of represents the average rate of change of the function. right? But if you think about it, we need to be able to define all these things before you even think about moving on. What I'm going to call this line from now on is a secant line. So a secant line is any line that joins two points together. But the characteristic feature of this line is that it's going to be related to a curve. So we know that there's a curve from point A to point B, right? We've talked about this several times in this video. And we know that A and B, when the function goes from A to B, the value of the gradient is changing. But what we're trying to do is find an average rate of change. On average, how is the gradient changing? How is it reacting? How is it going to behave as we move towards the other part of the curve? That would, ladies and gentlemen, be represented by FB minus FA divided by B minus A. This thing I wrote right over here. And this would be referred to as the average rate of change of a function. So what I'm basically saying is that the secant line is basically going to be equivalent to the tangent line at this point. That this statement could be misinterpreted, but what I'm saying is the underlying statement over here is that the slope of the secant line is going to be equal to the slope of the points of the given points, basically, in this case. And not just the given points, the tangent line that forms between these two given points. So this line is going to be called the secant line from now on, and this is going to help us in trying to determine what your derivative is. And when that time comes, you guys will see how important this statement is for a curve especially. So let's just do a particular example to illustrate what we've just understood, right? So we have a function f of x that's going to be represented by x squared plus x plus 1, and what we're trying to determine at this point is the average rate of change of f. And the given value for x is, well, 1, 3 and 313. Now they might give you the values of x in this case, but that's not really hard for you to determine the values of y over here. You could simply plug in the values of x over here and get the resulting values of y. So that's not really an issue at this point. So we know that the curve is going to look something like this. It could look like something different. You guys could plot it. If I were to look at it from a distance, this forms a shape similar to the x square curve, something like this. So but for simplicity, we're just going to assume it looks something like this, because it's going to kind of help us in determining what the secant line is going to look like. So this is what the secant line would look like in this case. And of course, we have a value 1, 3 over here, and we have a value 3, 13 over here. What we're trying to determine is the gradient of this line that I've drawn, the dotted line, not this part, the parts that are curving, because we can't really find the gradient of a curve as talked about previously, right? Because the gradient of the curve is changing at every point. So if we were to find the gradient of this point, it would represent the average rate of change of a function, of course, right? So let's find that. Let me just get this out of the way. Right. So that's going to equal to delta f divided by delta x. And delta f in this case gives me 13 minus 3, which is f of b minus f of a, divided by 3 minus 1. And this gives me 10 divided by 2, that's basically 5. So what is this representing? This is basically representing the slope of the line that joins this and that point. And it represents an average rate of change for this particular function. So basically in the next video, we're going to be talking about how to define a derivative, or basically what is more popularly known as an instantaneous rate of change, which over here we're talking about the average rate of change, right? So that's going to be very specific, and it's going to talk about the instantaneous rate. And let's see what we can do with that, and hopefully you guys will kind of get the concept of a derivative. See you guys in the next video.